Hello everyone, I am Belal Hossen, a civil engineering grad student at University of Maine. Today I am going to present Project 2.9 under Research Thrust Area 2, and this project is supervised by Professor Aaron Gallant and Professor Wardha Ashraf. Now I would like to talk about rapid cementation of soils via carbonation, challenges and opportunities. In recent years, the global CO2 emission has increased significantly in the world, and that's why scientists around the world are trying to develop new technologies that can capture carbon dioxide gas from major sources. For example, coal power plant, cement or lime manufacturing plant, and processed it in a industrial facilities for further utilization and storage. This concept is commonly known as carbon capture, utilization, and storage, CCUS in short. And our project is greatly motivated by this concept under the impression of applying it in geotechnical application, for example, soil stabilization and ground improvement. For any roadway infrastructure development, we always need to do some kind of stabilization or ground modification. In such chemical stabilization, using cement or lime or mixture of both is most common to increase the soil strength and stiffness. Here, a typical roadway subgrade stabilization process is presented. At first, we need to provide cement and water into the existing ground before mixing or blending them all together. Afterwards, we need to compact them to achieve the desired target degree of compaction before doing the final grading. And in case of wet curing, we need to provide water before doing the final paving works. However, in these methods, especially for lime stabilization, the chemical reaction through pozzolanic action is quite slow, which takes almost 28 days or so to gain the desired strength in the field. And both cement and lime are associated with high carbon footprint that consumes significant energy and also produce CO2 emission into the atmosphere. That's why our project aimed to develop a sustainable cementatious method that can be called as soil carbonation. And in that process, we can actually adopt this existing methodology in addition to one additional step, that is introducing carbon dioxide gas. And I'm going to discuss more in the following slides. Now, soil carbonation is the process of introducing carbon dioxide gas into the soil in presence of water or in presence of water and alkaline sources, for example, calcium or magnesium oxide and hydroxide. And upon chemical reaction between these three, it can precipitate carbonate binder on the soil grains that can cement the soil and increase the strength and stiffness. Now, in terms of soil minerals, sometimes it is commonly available in some soils. However, Maine soil is alkaline deficient. For example, we do not have any calcium or magnesium source. That's why our project considered calcium-based mineral, that is hydrated lime, and that need to be mixed into the ground before introducing carbon dioxide gas. Now, two potential benefits can be highlighted here. This process is quite instantaneous. That means we can improve the soil strength more faster as compared to our traditional lime stabilization. And secondly, this process is consuming carbon dioxide gas, which can be captured from the industrial source. That means this process would be more sustainable and environmental friendly. Now, the soil carbonation, that means the CO2 gas flow through lime mixed porous media is dependent on initial soil state. That means water content or void ratio. In terms of water content, if the water content is too high, that means the gas diffusion process will be very slow and it will slow down the chemical reaction. On the other hand, when the water content is low, chemical reaction will not occur. That means there is an optimum initial state of lime mix soil that need to be investigated for carbonation to increase the carbonation efficiency. Now I would like to present a qualitative assessment of cement, lime, and carbonation using lime as an alkaline source to quantify the carbon footprint. For any ground improvement construction, we can calculate the carbon footprint associated with that method using a method called CIAM. Now here I am focusing on materials carbon dioxide production, and based on that I would like to compare these three methods CO2 emission. Now we considered that we have to treat 1 ton of soil which will have an appreciable amount after treatment, and in order to have that appreciable strength, for example 2 to 3 MPa, we have to mix 10% lime or cement by weight and see how much CO2 emission can happen. So in terms of cement and lime stabilization, we can see that the CO2 emission is almost 0.1 and 0.09 ton per ton of soil treatment. Now, having same amount of lime mixed with the soil, and if we do the carbonation, we can reduce CO2 emission by 67% when no CO2 loss occurred and full carbonation happened. Meaning that if we carbonate lime mixed soil, we can actually reduce the significant amount of CO2 emission. In terms of methodology in our laboratory investigation, following the field implementation, we mix soil, lime, and water together and prepared the reconstituted specimen and then transferred into a carbonation chamber for designated carbonation period. Once the carbonation is done, we perform the unconfined compressive strength to see the strength improvement and also did thermogravimetric analysis to quantify the calcium carbonate binder formation after carbonation. Now I would like to present some results based on our preliminary investigation. This figure shows the effects of initial degree of saturation on degree of carbonation or binder formation of 10% lime mix sand that were prepared at different initial water contents having the density constant are carbonated between 3 to 168 hours. Now we can see that as the carbonation time increased, the amount of calcium carbonate binder formation is also increased, and the optimum binder formation is occurred when the degree of saturation is around 50%. Once it goes more than that, so for example, if it is 80%, it reduces the carbonation significantly and increase the carbonation time up to 168 hours to have same amount of binder formation in the soil. Now the left figure is showing us the binder formation with time at different degree of saturation, while the right figure is showing the strength improvement with time for the same degree of saturation specimens. Now we can see that the UCS is increased with time as the binder formation is also increasing, and it can achieve almost 3 MPa of strength in 3 to 5 days, having maximum binder formation. So the strength development for any particular void ratio or density, the strength is highly correlated with binder formation. And we also see, based on this developed relation, where the strength is proportional to binder content for this initial density or void ratio. So the strength of carbonated soil is dependent on binder formation for any particular void ratio. Now we also studied the effect of void ratio on binder formation and carbonated strength. Here specimens were prepared at 2 different initial water contents that were carbonated between 24 and 168 hours. So in terms of binder formation, we can see the effects of void ratio for any particular carbonation time is less pronounced. However, if we see the results in terms of degree of saturation, we can once again see when the degree of saturation is around 50%, maximum binder formation occurred. Now, in terms of carbonated strength, the interesting fact is once the void ratio is increasing, that means the density is reducing or relative compaction is reducing, the strength is reduced significantly from 3 MPa to 1 MPa or so, although they might have similar binder formation as you can see here. So the strength of carbonated soil is dependent on maximum binder formation and maximum dry density. Now we also looked at this carbonation and the state dependency concept on silty material. So we all know that silty soil are frost susceptible, especially in New England region. It has serious impact on transportation infrastructure. And in terms of results, based on state dependency, we have similar observation for silty material. And we found out that when 10% lime mix silt is fully carbonated, having minimum void ratio with maximum dry density, we can obtain strength as high as 3 MPa. And that means this soil carbonation concept can be applied to stabilize the frost susceptible soil, and which will improve the durability and infrastructure performance in our New England region. Now, in terms of implementation of this concept for shallow stabilization, as I said, we need to mix the alkaline source, that is lime in this case, using the existing technology, as I have presented before and you can see here. And after mixing the lime and doing the compaction, we have to install some perforated pipe through trench excavation. And following that, we have to backfill it and then introduce the carbon dioxide gas from a source stand like this. And this facility, that means the CO2 can be bring on site from a commercial company, which is currently available right now. So in order to understand this proposed methodology, we are planning for a larger scale soil box testing to understand the field performance, considering the CO2 loss and the maximum carbonation time required to gain the strength what we observed in our laboratory scale. And we also need to understand what's the binder uniformity and associated strength improvement to have the optimum performance by distributing those perforated pipes. So in summary, I would like to conclude that based on the results, it is clearly revealed that accelerated carbonation of lime mix soil is an innovative and emerging sustainable soil improvement technique, which can store the carbon dioxide gas into the ground, and at the same time we can achieve faster strength improvement as compared to our traditional lime stabilization. In terms of carbonation efficiency, initial degree of saturation played an important role, where water content is more dominant over a void ratio, and the rapid carbonation is mainly occurred at degree of saturation 50%, and the maximum strength is associated with maximum binder formation when we have maximum density that corresponds to relative compaction more than 90%. However, having said that, still we have some challenges and that need to be resolved for shallow stabilization of soils. Now I would like to thank our Transportation Infrastructure Durability Center at University of Maine for providing the financial support and continuous assistance to execute this project. Now I would like to thank you all for your attention and attending this presentation today. Thank you.